Hello everyone, welcome back to CPE 517-WLS, Digital and Computer System Architecture. This is lecture 8, lecture 9, part 1, Vector Processor. So per our last lecture, we mentioned that instruction level parallelism has its limitations, right? It cannot go beyond CPI equal smaller than 1. If so, we have to try a very long instruction word or some very sophisticated advanced hardware. So this tells us one thing, that we probably ask the hardware to go too far. It's the time for us to think about offer some interfaces for the software to better, introduce hints for the hardware to deal with it. So what do you mean by introducing interface? That is new paradigms, like new parallelism paradigms. We don't only say, okay, you can think as this process is a single-threaded. We want you to think like this is a multi-threaded, this is a data-centric or single instruction model data. How will you deal with it? Okay. Why? Because first, there are a lot of data level parallelism applications we mentioned about last lecture, such as matrix-oriented, scientific computing, multimedia-oriented image and sound processors. And we want to try single instruction model data for data level parallelism, which is the same thing, right? So if you see you have data level parallelism, which means the data is the centric. So we say single instruction model data, what does it mean? Single instruction over data, right? And multi-data, right? So a lot of data. So assuming we have so many data here. Okay, so what we want to do is we try single instruction. All the data share the same instruction. All of them are like A0 plus B0, A1 plus B1, A2 plus B2, etc. Right? So it's the same instruction applied to so many data. So we call that single instruction model data. Well, this is very energy efficient. Why? Because we only have to fetch one instruction for all the data. Probably we have like millions or billions of such entries. We only need a single instruction to do it. This makes single instruction model data very attractive for personal mobile devices. SIMD allows programmer to continue to think sequentially. Why? Because we can think of A0, A1, A2, all of them as a single variable, right? Similarly for B0, B1, B2, all of them. So in this case, because we can think from the instruction perspective, it's really just a single instruction. This comparing to multi-threaded or data level or thread level parallelism, data level parallelism is much better, because if you think from the instruction perspective, data level parallelism is the same as single-threaded or serial version. Well, thread level parallelism introduces threads over there, so that introduces more complexity of thinking. In this lecture, we're going to discuss 3 important data level parallelisms. That is vectorized architecture, SIMD extensions of MIMD devices and GPU. Okay. For x86, let's see why we want data level parallelism. As we show here, for x86 processor, we expect 2 additional cores per chip per year. Well, SIMD width are actually projected to double every 4 years. In that case, SIMD will definitely be faster than MIMD in a short period of time, right? So first, let's discuss vector architectures. The basic idea of a vector architecture is that we read sets of elements into vector registers, operate on those registers. Oh, sorry, I forgot to mention about one thing. Okay, so the basic idea is like read sets of data elements into vector registers, operate on those registers, disperse the result back to memory. Registers are controlled by compilers used to high memory latency and leverage memory bandwidth, right? So I forgot to mention about this. So logistically, the slides, some of them adopted from David Patterson, some from Sen, and some from Howie. All the credits goes to original authors, and all recording and modifications might be made due to requirement. Okay. So this is an example about the vectorized architecture. That's Rev or vectorized MIPS, right? So Rev64V is loosely based upon part1. There are in total 32 64-bit. Okay, let's continue share. Okay. To 64-bit vector registers. Register file has 16 read ports and 8 write ports. We have vectorized function units for fully pipeline data and control hazards are detected. Vectorized load and store unit, fully pipeline, 1 word per clock cycle after initial latency. Scala register, we also have that, like 31 general purpose and 32 floating point. So this is the vectorized MIPS. If we do .vv, it means there are 2 vectorized operands. If it's a vs or sv, it means vector scala, right? LV, SV means loading vector and storing vector, right? Assuming you have this line of DXP in C, what we do is for every element of X, we multiply that with A plus a Y and put it back to a Y. So the way we do it is in the typical way is like this, right? So we first load an element of A, the value of A, and then we we put the address to load, right? So it's like X, okay. X5, we load from X. Multiply F0, which is A, and F1 is XI, and storing F1, and then we load Y, I, right? And then we add A multiply XI. So this is A. This is for X. And then loading X. This is multiplying A XI. And then this is loading YI. And then we add AXI. plus yi. And then this is a storing back to yi, and then we increment x, increment y. If it's not, oh, this is n. This is n. So in total, 32 elements. This is how we do computation for per iteration, one loop, right? What if we do vectorized, like we do 4 floating point operation per iteration? Load A, which is a scalar, and then load the vector is V load, right? Multiply is a vector and then we load the y and do addition and store it back. Disable. So in total, we need only 8 instructions to finish 4 operations. To 1, 2, 3, 4, 5, 6, 7, 8. However, we need to wait. So here, this is a 4 of 8 registers. So basically, here in total, we load 32 elements. Okay, and then in that sense, we have in total 1, 2, 3, 4, 5, 6, 7, 8. 8 instructions to finish the entire computation. However, for this one, you have to do 32 times of this loop. This loop contains how many instructions? 1, 2, 3, 4, 5, 6, 7, 8. So it's 256 plus these 2. That is 258. So we need 258 instructions versus 8 instructions to finish the same computation, right? Well, to achieve that goal, typically people do is using SIMD extension, like SSE or NVX. We use the multimedia applications to operate on the data types narrower in the native words. And then the limitation compared to vectorized instructions that the number of data operands coded in opcode, no sophisticated address moved, stranded and scatter gather, no masking registers. A vectorized computation can be implemented in last century, right? You have MMX, SSE, what I mentioned before. AVX, we're gonna give a tutorial, and AVX 512. The operands must be consecutive and aligned in memory locations. Roofline model Roofline model is a very important model for computer architecture. The basic idea is for the peak floating point throughput as a function of the arithmetic intensity ties together the floating point performance and memory performance for target machine. Basically, you can see here for different machines, they can achieve the arithmetic intensity is different, like for SPMV, sparse matrix space multiplication, PDE, lattice computation, FFT, plus n-body simulation. The computation intensity is different. One is constant time, one is log n, one is n. So roofline model is very important for us to estimate the peak performance. The attend the G-flops per second equals the peak memory bandwidth multiply arithmetic intensity versus the peak floating point performance. So basically say whether it's computation intensive or memory intensive. If it is memory intensive, then it would be this one to the peak performance. If it's computation intensive, it will be this one to measure the performance, right? Okay, that's for part 1. Then we're going to go to part 2.